Hello everyone, my name is Sunjae Kim, and I am a first-year undergraduate student at Dongguk University. It is a great privilege to be here today to present my research on a novel architecture for seismic energy harvesting. The title of my work is Multi-Axial Vibration Energy Harvesting via Torsional D15 mode Piezoelectric Conversion. As we move into the era of smart cities and the Internet of Things, the demand for autonomous, battery-less sensors has exploded, especially in seismically active environments where the grid may fail when we need our sensors the most. Today, I will walk you through our mathematical framework for a structural solution that captures chaotic, multidirectional vibrations and converts them into highly efficient electrical power. Let us begin. To understand our design, we must first confront the mechanical limitations of current technology. Most piezoelectric energy harvesters rely on a simple cantilever beam. When the ground shakes vertically, the beam bends, straining the piezoelectric material to create electricity. However, seismic waves are fundamentally multidirectional. They consist of P waves, which move longitudinally, and S waves, which move transversely. Here is the bottleneck. If an S wave hits a traditional cantilever from the side, the beam is rigid. It strikes the structure's neutral axis. The energy is not converted into strain. It is lost to impact resistance. Current harvesters are unidirectional. They only care about one dimension. But our seismic environment is complex and three-dimensional. That is the fundamental gap we are trying to close. To solve this, we turn to the fundamental electromechanical coupling coefficients of piezoelectric ceramics, specifically PZT5H. Traditionally, engineers gravitate toward the D31 bending mode. It's simple and it's well understood. But look at the coefficients. The D15 shear mode, or torsional mode, offers a piezoelectric constant that is nearly 3 times larger than bending. Why does this matter? Because electrical energy generation is proportional to the square of the piezoelectric constant. This gives torsion a massive theoretical advantage in power density. Furthermore, consider the geometry. In a bending beam, the exact middle of the material is the neutral axis. It does absolutely nothing. In a torsional cylinder, the shear stress spirals evenly around the entire outer volume. We are straining 100% of the active material. The engineering challenge, then, was to find a mechanism that forces chaotic, linear, 3D vibrations into this efficient, uniform torsional strain. This leads us to our architecture, the cone slit harvester. Our design features a vertical piezoelectric core surrounded by a heavy outer mass. The coupling is defined by two variables, the cone angle and the slit angle. Let's look at the vector kinematics. When a horizontal S-wave acceleration hits our mass, it generates an internal force, Fh. If the base was a flat cylinder, that force would just vanish. But by introducing the cone angle, we force that force to project along the slope of the cone. The force becomes F slide equals Fh times cosine theta. But we are not done. That sliding force needs to twist the core. That is where the helical slit comes in. Tilted at the given angle, we convert that sliding force into a vertical torque. The final vertical driving force is F vertical equals F slide times sine theta. If we multiply these, the final vertical driving force is proportional to cosine theta times sine theta. By using the trigeometric double angle identity, this is exactly half of sine 2 theta. This is why the math mandates a 45-degree angle. When theta is 45 degrees, the sine of 90 degrees is 1. We have mathematically forced the geometry of the device to capture the absolute maximum energy of the seismic vector. To validate this behavior dynamically over time, we formulated an integrated governing differential equation. We modeled the incoming seismic waves as harmonic oscillators, converting their spatial ground movements into time-dependent acceleration profiles. Let's unpack our master torque equation term by term so we can trace the physics completely. First, look outside the bracket. The variables m and large m represents the mass and radius of our outer shell, which acts as our fundamental scaling multipliers. Next to it, the terms sine theta, cosine theta represent our mechanical slit coupling coefficient, which dictates how the vertical motion is resolved into rotational torque through the helix. Now let's look inside the bracket, where we see how our design splits and processes the two wave types. The first term represents the transverse S wave. Here, AH is the horizontal wave amplitude, and the quantity 2 pi over TH squared represents our squared angular frequency. Notice that this entire horizontal acceleration term is multiplied by our wedge projection factor, cosine theta sine theta, which we just proved peaks at 45 degrees. The second term inside the bracket represents the longitudinal P wave. Here, AV is the vertical amplitude, and 2 pi over TV squared is the vertical angular frequency. Notice a critical details here. Because the P waves moves vertically, it acts in parallel to our central shaft and completely bypasses the cone slope modulation. By taking this master torque and subtly substituting it into a second-order torsional equation of motion accounting for our core's polar moment of inertia, J, its mechanical damping, C, and its torsional stiffness, K, we constructed a state space model. We utilized MATLAB's ODE 45 solver to compute the exact dynamic angular velocity and evaluate the continuous electrical power yield over time. To evaluate this dynamically, we formulated a state space differential equation and ran simulations using MATLAB's ODE 45 solver. These heat maps show the efficiency across all variations of our two angles. As you can see, the hot spot, the optimal performation zone, is exactly where we predicted, at 45 degrees for both variables. But simulation is one thing, comparison is another. This graph compares our 45-degree design against a standard 90-degree cylindrical harvester, shown here in magenta color. The difference is stark. The control group flatlines. It cannot convert the S-wave energy. Our optimized geometry, however, successfully recovers that energy. This proves that our design is not just a theoretical exercise. It is a measurable improvement over the status quo. To validate this, we tested our model against the earthquake that happened in 1940, the El Centro earthquake, which is the gold standard for structural engineering. With a peak ground acceleration of 0.34 g, our harvester generates a peak output of 1.5 milliwatts. Is that practically useful? Look at these requirements. A MEMS wake-up receiver requires only 50 microwatts, and a structural accelerometer requires 180 microwatts. We don't just clear these thresholds, we clear them with room to spare. While high-power telemetry like the GNSS units require more energy, our system generates enough power to run 8 seismic sensors simultaneously. We are essentially using the earthquake's own destructive energy to power the warning systems that keep. This slide addresses a vital question regarding real-world viability. Does our harvester require a catastrophic disaster to function, or can it act as a true early warning system? To find out, we calculated the absolute minimum seismic threshold required to wake up the system. Our target milestone was a standard MEMS structural accelerometer, which requires 180 microwatts to boot up. The results show that our harvester hits this power target at a ground acceleration of just 0.11 g. In real-world terms, this correlates perfectly to a moderate magnitude 4.5 earthquake on the Richter scale. Because a 4.5 magnitude earthquake causes less structural damage, this result proves our device is sensitive enough to boot up, initialize safety sensors, and broadcast emergency data during the first minor foreshocks, buying life-saving seconds to trigger automated building isolation before the destructive main waves arrive. Here are the references. Keep us safe. In conclusion, our research demonstrates that the highly efficient D15 torsional mode can be successfully accessed for chaotic ambient vibrations through the geometric conversion. Our next step could be to fabricate a physical prototype and validate these models on a laboratory shaker table. Thank you very much for your time and attention. Now I will be happy to take any questions.